Carlos Barcelo, who will talk about the emergent gravity pursuing an idea. Please.
Thank you. First, let me thank the organizers for giving me the opportunity to listen to such interesting debates. And this talk is different from the ones that you have listened. I'm not a philosopher, I'm working in physics. And but I hope that it would resonate with some of the ideas that we have been discussing. So the plan of the talk is that, first of all, I will describe what do I call here, when I say about emerging gravity, I will call emerging gravity to one specific thing. It's not, for fixing the ideas of what I'm going to call, I will present an example of what I'm calling an emergent theory of gravity. And then I will pass to describe why I think this, to exploring these ideas is interesting for me. And within this interest, I will show one thing that can come up from this analysis that I think is interesting and it has a direct application in astrophysics. And finally, I will pass to sort of put a lot of questions that people should answer, or I should answer, if in order that a theory like the one that I'm going to present is going to work or is going to be a proper quantum gravity theory. And I will not answer these questions, but I will at least say a few words about which are the kind of responses that I think might be the ones that are relevant. So this is just for fixing ideas. It's what do I call an emergent gravity theory? So what I call an emergent gravity theory is a theory whose elementary constituents do not have much bearing on the characteristics of general relativity. So here, the thing is that as I'm going to describe things, it's like a reductionist program, if you want. So we are going to see whether there is some basic constituent from which you can have at some regimes in which you have something that is, for example, general relativity. But the thing is that this general relativistic behavior, one thing that for me is important in the case of calling something emergent, is that it's difficult to predict theoretically. It's something that because there is a huge gap between the ingredients that you use to define your basic theory and the ingredients that are resulting in the general relativistic view. So from this perspective, this I qualify this because the emerging gravity and many approaches of quantum gravity, they say, well, this is emerging gravity. So I'm distinguishing my personal take from other takes, saying that from this perspective, for example, loop quantum gravity would not qualify as an emergent gravity theory, all dynamical triangulations and causal sets, because, as I said, they are taking a lot of ingredients in their own constructions that are coming from what we know about general relativity already. Instead, for example, string theory, it would be closer to our definition in the sense that, for example, people was not working on a string theory because it was a gravity theory. The gravity appears there, but because someone realized it. But it was not that it was built in this orientation. So in this sense, this string theory will be closer to that. And the one that I'm going to present is even closer to that because it's tried to take even less ingredients from the final supposed theory. So when I was starting to try to fulfill this program, I said, well, this is very complicated. To find a complete theory of quantum gravity the setting that I'm going to describe is a setting that is based, I will mention it later, it's a very simple setting in which is trying to find a quantum gravity theory within standard quantum mechanics of many bodies, meaning a condensed matter system in which you define a condensed matter system in a Newtonian world. So you have time, you have space, Euclidean space, and then and you have pieces there. You have atoms, And then from there, you have to you want to see whether it is possible to build up a quantum gravity theory. So because this particular program is, I can assure you that it's difficult. I said, well, let's first try to see whether I can do the same thing with a more simple system. And then what I try to do is to produce an emergent theory of electromagnetism, of electrodynamics. And this is what I'm going to present in the next slices. So what I'm going to present now is, I understood that in a sort of training towards this more complicated stuff. Then as a working hypothesis, I mentioned here that there is this Newtonian world. So this is there at this stage. But I understand this specific stage as the simplest. Once you have something that has dimensions, has a continuum of some space and some time, the thing is that, which is the simplest structure that you can give to this without putting too much structure on that. And I say, I think that the most intuitive is this Newtonian thing. Is that so you don't impose, for example, you don't impose that there is any fixed velocity for the transmission of signals or anything. Things can travel to the velocity that you want. So there is, and again here, just to mention it, is that I'm assuming also that quantum mechanics. I mean, I'm not deriving quantum mechanics. I assume that quantum mechanics is there. Okay. So now there is a few slides that I'm going to be quick, and it's just to give you a flavor about the formalism that I'm happy developing. So what I'm going to show now is an example of a theory of emergent electromagnetism, electrodynamics, and it's built. It's inspired in works of a famous condensed-matter physicist, theoretician, is Richard Holovic. And the idea is that you have, as I said, a many quantum particle system that is built up from spin to spin 1/2 particles. You don't know what they are. These are not real. It doesn't need to be real atoms. And then you say, well, let's analyze a theory in which, regarding the low energy properties, it behaves like this. The thing is that, first of all, people in condensed matter, they know that there are many theories that fulfill this. There are strongly interacting systems. This is, many of the ideas are coming from working in helium-3, instead of fluid phases of helium-3. And then what you see is that the helium-3 is a strongly interacting system, but in many of the properties, it behaves as a really quickly interacting systems in which you change your initial atoms by rest atoms. So at the end is that even though you work in a it seems that it is a very specific theory, but from the start, this theory represents a class, a huge class of theories that can behave essentially like this. For example, as I said, a very dilute gas behaves like this, but a very strongly interacting gas also behaves like this. And then, which are the main ingredients to go towards obtaining an electromagnetic theory? The thing is that it is necessary that the interaction between the atoms, you have to prescribe a sort of interaction. And it is important that this interaction has a repulsive core. So it has to have a potential of this sort. And then, by assuming that, well, this is a different way of describing the system in terms of, this is the Hamiltonian, described in terms of creation and destruction operators. So you have these kinetic terms and then these interaction terms. But as I said, if you have questions about that, you will ask me, but I was trying not to. So once you have this, it happened, we know that it happened, it can happen that the state of the system at very low temperatures, the backing state of the system is such that it condenses. And there is a specific sort of condensation, what happened in helium, which is called P-wave condensation. P-wave condensation is a condensation so that, which is precisely because this repulsive core in the previous slides, The thing is that the Cooper pairs, you have two atoms that instead of being with the states that are arbitrary, they tend to go together. No? And then the thing is that because they cannot combine, because the repulsive core, they cannot combine in the S state, in the quantum state described by isotropic quantum numbers. It has to condensate in these P waves. And this P wave means that you have a specific direction, you have a vector, because you have an L, in terms of quantum mechanics, you have an L state, L equal 1. And this, so there are several phases in which this condensation can happen. And there are two, and the one that I'm going to describe is the planar phase. But here I describe mathematically how is the planar phase, but more simple terms, well, in the ones that have been observed already in condensed matter laboratories are the A phase and the B phase. These are already, but then if you go to the helium-3 phase diagram, you see that these two phases these are the normal phase of helium-3, this is the A phase, the B phase. But then there is conjecture, well, formally it appears on the P phase, people say that it should be here in a small band. And they are close to see in some specific systems to really see that the presence of these phases. It has been predicted, but I think that right now it has not been observed. But what from my point of view here is that because the atoms are not real helium atoms, it's something that you just prescribe. What do you want the behavior? What interactions do you want? The thing is that there are ways to make the planar phase to be the one that is adapted when you lower the temperature of the system. So again, the important point is that the planar phase, it can be described as a combination of an L vector, orbital spin, orbital momentum of the pair of atoms, plus the spins. Well, the thing is that in the planar phase, what you have is that two spins, two atoms, when they are like this, the angular moment, they rotate in this way. And when they are like that, they rotate in the other way. So that, and this is the planar phase. So at the end of the day is that you have two different possible directions for the spins and two different directions of the angular momentum. What happened there, the difference of the P phase with respect to A phase is that the A phase is really axial. That's why the name A is axial, meaning that there's always one vector. Here, if you want, the planar phase is not defined by a vector. It's defined by a line in momentum space. Okay, this is probably a bit too technical, but the thing, let's try to see. Now, once you have a vacuum state, is that you lower the temperature of this system, and then it tends to create a vacuum state, the state of minimum energy, which is this planar phase. So you have this condensation. On top of that, you have to analyze which are the first excitations, the lowest energy excitations that you have in the system. This is the way that people, and then you have to analyze the equations of motion of the first excitations on the system. So you do an analysis, and then you realize that because the specific characteristic of the planar state, you have this system exhibits Fermi points, meaning it has two Fermi points on the specific line in which these atoms have condensed. So you have a line, and then you have two specific points in momentum space, these two things. So if you have a momentum space, so you have one you have a particular direction that it can be X or Z, and then you have plus something and minus something. And there you have two specific points. Fermi points means that if you produce an excitation which has a momentum which is very close to these points, the energy that you need to excite this mode is very close to zero. It goes to zero. Instead, in the normal situations, you have these energy gaps. Is that in order to excite something, you have to introduce some specific amount of energy. So, when you see this, then you realize that if you linearize what happened, because all the physics at the end is driven by what happened at low energies. And then the modes that are the ones that are more excited are the ones that are controlling the physics. And what you see is that these modes are following this dispersion relation, which is, you are familiar with this. This P is the perturbation, this P calligraphic, or this quotic, is the perturbation with respect to the Fermi point. And then what you see is that they follow a dispersion relation which is relativistic. It's the same one that you will get in Minkowski system. And you have some definitions. And then the thing is that because you have these two Fermi points, the form of the excitations, you have to exhaust the number of excitations that you have there. So at the end, what you find is that there are two different sorts of excitations. There are that formally are spin are neutrinos, because the system has the system, as I said, the basic system is spin 1/2 things. Now what you have is that on top of the vacuum state, you have waves, spin waves. These are the excitations, spin waves. But these spin waves can have two different helicities. And the spin waves have, because they are spin waves, they have 2 degrees of freedom. And so you have 2 degrees of freedom, but then you have another 2 degrees of freedom because some excitations are coming from one Fermi point and other excitations are coming from the other Fermi point. Without trying to be very, the thing is that you finally can prove that the final equation that is satisfied by the excitations in the system is precisely a Dirac equation with four-dimensional spinors, without a mass here, because then the mass should be introduced later on if you want to have mass. But the thing is that the excitations of the system are precisely that. And this equation is undistinguishable from an equation, a Dirac field in a Minkowski system. It's precisely a Dirac field in a Minkowski system. This is a very nice thing, is that the emergence of charge in these systems is very nice to see that there is a notion of charge immediately there, because the excitations between these that are living in this Fermi point and the ones that are living in this point, at some point you don't distinguish that because you don't see that. In your low energy physics you cannot see this space-time, this structure. What you see is just that there are two different sorts of excitations that are having some momentum, and the real momentum that you can measure is this one, it's not this one. So at the end you have kind of two sort of things living with you. And some of them you call electrons and some of them you call positrons. So once you have, so this is the last ingredient, sorry because this part probably, the following parts will be more argumentative, but this part is trying to say that first we have the vacuum, and then you have the excitations of the vacuum, and then once you have the excitation of the vacuum, you can also analyze which are how the excitations modify the very structure of the vacuum. Meaning that the vacuum itself, because if you don't do anything, then the state is the vacuum. But if you put in some part of this system, you put a spin wave, is distorting the way in which the vacuum itself is distorting the pairs that were forming the vacuum itself. And then you can analyze how is this distortion. And now I will pass very quickly here. The thing is that I will go directly to the final result, is that when you end up analyzing what happened with the perturbation to the vacuum, what you see is that you can describe the perturbations to the vacuum by changing your original equation, now the Dirac fields, instead of living in just in Minkowski space, now they are living in Minkowski space, but they are interacting with something that is acting as an electromagnetic field. So the electromagnetic field is just the perturbation of the orientations of the definition of the characteristics of the vacuum state, which is this planar thing, is that you have a vector and the vector oscillates. So the oscillations of the vector that define is acting as an electromagnetic field. So the next stage is that once you have that, you have already a theory in which you have an electromagnetic field plus Dirac electrons. And then the next stage is to see which is the dynamics of the very electromagnetic field, because now it's just kinematics, but then you have to see whether the dynamics is preserving some sort of Lorentzian symmetry. So now the thing is that because the particles that are forming, they are distorting the very vacuum, are Lorentz invariants, because you have this Dirac equation. The thing is that this symmetry is inherited by the very fluctuations of the vacuum. You can see that, for example, as thinking that the photon is just a pair of the spin waves. So the spin waves are traveling at the speed of light, but then a photon is just a combination of two of them that is making a spin one thing. So the photon is this coherent combination of the various spin waves. At the end of the day, one way to see this is this, for example, I think I will describe it because I think it's interesting. Is that imagine that you just say, well, I have these A's, so let's try to build up the most general thing, which is Lorentz invariant, because this inheriting symmetry. And then you build up this, and then you say, well, imagine that there is now this M, which again, it depends on the characteristics of the system. But imagine that this electromagnetic field doesn't have a mass. Then you have this theory. Okay, this is a standard electromagnetism, it will be gauge invariant, but this is a term that breaks gauge invariant. You can prove that this theory, the one that has these two terms, does not have gauge symmetries, but it has a physical symmetry which you can change the electromagnetic field by these things, but you have to impose a condition on that. If you impose a condition on that, then you can show that this is a real symmetry. The conserved charges of the system are not vanishing. So, but you have in fact, you have an infinite number of symmetries which are not gauge. It is not the same to say that a system has infinite number of symmetries, that it has gauge symmetries. So once you do that, in fact, in this theory, you can calculate the stress energy tensor. And the stress energy tensor, it has the Maxwellian part, and then you have additional parts. And then what you see is precisely that by changing these symmetries, you see that different solutions, they have different energies. So it's consistent with the idea that these are not gauge symmetries. So you can distinguish between these symmetries. But then it's a funny thing, is that if there is an equation in this system, there is an equation which is that, and there is a combination of the A's, which is, by assuming charge conservation, it leads to, in the theory, there is the presence of a free field. So if this free field, you decide which is the specific solution for this free field, and you say, well, because there is nothing that can excite this, let's put this into zero. If you put this into zero, then all these terms disappear. And then what happens is that in a particular sector of the entire theory, you have your entire theory, which is not gauge invariant. But in a particular sector of solutions of this theory, it happens that all the observables that will be able to distinguish between different solutions are not able to distinguish. So, and then, and the charges, all of the charges that are not trivial, if you impose this condition, then all the charges become zero. So once you realize that, you say, well, it doesn't matter whether I'm analyzing this as a theory which doesn't have any gauge invariant, but is precisely in the sector of the theory in which this particular field is zero, that to analyze a gauge invariant theory. So this is a way to see how a gauge symmetry can emerge in a system that doesn't have any gauge symmetry from the start. It has, so from here what you is a proof that just by starting with Lorentz invariance, you can have emergence of gauge invariance. It's very close. I mean, from Lorentz invariance to gauge invariance is not that far. So, a few observations here. I have already finished the hard part. So, a few observations here is that here in this way of understanding this theory is that you see that there are these waves that are moving in something, but you will say, well, if there is, in the moment in which you don't have fields moving in your system, you would say that there is some Minkowski space there. I will not say that, because this is in a vacuum state that doesn't have any property that is related with anything spatio-temporal. But the thing is that once you have some fields, these fields move in a way that allows you to recover something that for you is kind of a space-time. So in a sense is that at this stage, space-time is just the way in which you encode the behavior of the fields. So I am, as I said, I am very much into these Brown ideas. For instance, in the case of special relativity. And again, I have also one work in which if you assume that your very low energy ingredients are the ones that are building up the objects that are themselves trying to understand the system, that if we are objects that are built up by quasi-particles, excitations in a system, the thing is that if you build up an interferometer with quasi-particles, this interferometer will not be able to see whether the interferometer is moving or not with respect to the real vacuum that an external observer is seeing. There is someone that defined, it has this laboratory, this helium like in a laboratory, and he knows that this is not moving, that the atoms there do not have any flow. But then an internal observer armed with an interferometer, which is not built by an external means, it's built by ingredients within the system, so it will not be able to know whether it's moving or not. So in a sense, is that you have all the ingredients to build up an internally consistent electrodynamics. So, stops. Let me continue here. So why to explore these arenas? What I was, well, the thing is that for me, they start to be interesting, but in general terms, because in a sense there are principles that we have been distinguishing this also in some talks, is that some theories are principle theories, is that you impose something and then you work out many consequences and you check whether these are true or not in nature. Of course, there's explanatory, but there are other questions that you cannot answer in these theories, in the principles themselves. Instead, if you get rid of some things, then you have ways to understand why this could be this way or this other. So, and here there is questions that you can ask in general, and that this way of building up theories can give you some potential answers. Why is there a speed limit for the propagation of signals? So when you see how these things work, what you see is that the propagation, everything, if your ingredients, what you call objects, are quasi-objects, meaning that they are building already from something else, it's unavoidable that the very notion that you need is a sound speed. It's not the only objects that are moving at arbitrary velocities are the ones that are fundamental. But if you build up from some fundamental things, even if you don't impose to the fundamental things to move to specific velocities, if you then worry about how there are movements involving combination of things, then immediately you get sound velocities. And again, there are different things that you can ask yourself, and here there are potential answers. Other things that are for me interesting is that they challenge some popular ideas of other approaches that are trying to get quantum gravity theories. Is that, for example, I'm not very much into the idea that only mathematical consistency is going to be able to show a single theory. Or so this, for example, as a proof of principle, is telling you that this electrodynamic emergence is based on a completely, this construction is already taking into account a lot of theories, of microscopic theories, because the only important thing is the symmetry behavior at low energies and not the specificities of the theories. And one of the things that I probably like the most is that is touching this empirical incoherence that were described by Vincent, Chris. Is that for me it has always been very disappointing that when you work in quantum gravity, it's like people is very committed in one tendency or another, but the thing is that it's very difficult for them to say, tell me a specific prediction, a strong prediction that you can give, so that someone that is trying to see experiments is going to be able to know whether string theory is correct or the other theory is correct. The thing is, for me, this is not at all clear that this is possible, because as you were mentioning, for me, very completely, is that that in a sense you already need that at the same time you have some emergence of some spatial temporal things very close to the ones that we are used to in order to and then by working in this style of theories, the thing is that you change the emphasis between the compromising of commitments with the specificities of the details of the theory, instead to some general features on how from microscopic constituents, in which you try to impose as the least structure possible, which are the things that are surviving at the microscopic level. And then, for me, the important thing is that I'm very much into semi-classical physics in a sense, because it's like if I see that there are these sets of theories, microscopic theories, that first of all they go for general relativity, but then next to general relativity they start to say, well, the first deviation from general relativity that are still not very much dependent on the details, these ones are the ones that I would trust more in order to guide the observation and to see. And I think that now we are still to a stage in which we are very far from really empirically testing specific proposals. But maybe we could try to test not so detailed proposal, but some specific generic features. And now, how much time do I have?
About 10 minutes.
About 10 minutes. So I will go very quickly through here, and then I will go, because this one probably will be less interesting for you, but I will just mention this, and then I will pass to the questions that maybe will be more interesting. The thing is that, for example, by working in these things, I'm also working, well, having always working in this in black hole physics and trying to understand physical aspects of quantum gravity in this setting, in black holes. So the thing is that one of the things that I have been trying to tell people is that the existence of the singularity in a black hole, if you do something to the singularity of the black hole, the rest of the physics that surrounds the entire systems is not very robust. Is that different proposals for what happened in the singularity can lead to absolutely different physics. And in particular, by looking at these ideas of trying to see if a theory along the lines that I was describing before, but for gravity, there is something that for me is kind of generic that these theories tend to tell you. And it's that there is a scale at which gravity should switch off. It's that gravity should not be always there, because gravity will be associated as electromagnetism to the condensation of some coherent things. Is that the physics has some coherent fields, but then you have some quantum fields that are the excitations. And the coherent fields are the ones that are representing bosonic fields, that are the ones that are able to coherently behave, because there are bosons. And then gravity has this same notion. So the thing is that it is possible, or at least it's a possibility, a large possibility, that that when matter, when you try to probe very high energetic situations in black hole physics, at some point, what is acting as curvature would disappear. But instead, the Minkowskian structure, the causality based on the very excitations of the, for example, in this case, of the fermions, of these spin waves, this survives even beyond the place in which your very coherent thing starts to blow up. So the thing is that it would be, so by following these ideas, we were proposing geometries in which you say, well, imagine what would happen if gravitational collapse is such that it leads to these geometries. And these geometries is just representing that a black hole, instead of really going into a singular thing, close to singular, that is something that is acting as a sink, even though maybe it's regular, or maybe it's a ball inside, whatever. But then you have a horizon, and the horizon is living forever. Instead, what we say is that what happens is that if the black hole, instead of that, is just turning into a white hole in very fast. In fact, for astrophysical numbers, this gives numbers that are because this goes with the crossing time of the internal structure. So it's microseconds for the collapse of a neutron star or something. And then we were starting to analyze the geometrical properties of such a proposal. And then you see that it is only necessary that there is a region, a quantum region. This is a classical solution of GR. This is a classical solution of GR. But then there is a quantum region in which there is something that acting as an effective stress energy tensor which violates energy conditions. And it is necessary that it reaches some point outside the very horizon. So, well, it's a proposal. At this stage, is just, if you want, it's just an empirical, is that I don't have a complete theory that predicts a dynamical theory substituting gravity that leads precisely to this solution. But I said, well, it's a possibility. And the thing is that if, and within this paradigm, you will have completely different physics. In fact, just to describe this, what you would have is that you have a neutron star that collapses. It forms something that for you, for some moments, it's very similar to a black hole. But then, instead of staying there, it becomes gray, it becomes white. It comes back to kind of the same initial position, but because there is dissipation in the process, instead of going to the same initial position, it goes back not to the very initial radius, but with a shorter radius. And then it goes back to collapse again. In a few cycles, the thing is that, funnily enough, the quantum state of, in the same sense of Hawking evaporation, what happened with the normalized energy momentum tensor in geometries like that has not been analyzed. And the thing is that when you analyze this, there is a huge possibility open that once you do a few cycles, that as again, it's taking less than a second, it's still, we are in the millisecond range, that finally you end up with something that is very close to the formation of the horizon, but is not able to do it because there is specific pressures, quantum pressures, that do not allow to continue with the process. And this is the very, this can be dealt with the normalized stress energy momentum tensor. Because the stress energy tensor, what is well known is that if you have something if you have something that starts from a neutron star and you follow the behavior of that, because this is very quick, the normalized energy momentum tensor doesn't have time to grow big enough to modify the very structure of the collapse. But instead, if the very collapse started from something that is already very close to the, which is already very close to the horizon, then the normalized energy momentum tensor starts to grow and grow and grow. So there is, as I said, there is an open possibility that these things, and this is one of the issues that we are working on, is the phenomenology of a transient phase of something that when you see something collapsing, some sort of supernova forming a black hole, the standard paradigm is that a supernova forms a black hole. What we say is that instead of forming a black hole, you form something that has a transient in which you have an oscillation, a very rapid oscillation between black hole and a white hole, and then it settles in something which is something that is mimicking the physics of a black hole, and that is an ultra-compact star, but which is outside the very horizon. And the nice feature of that is that this immediately leads naturally to a modification of the pattern of the gravitational wave emission pattern of this is one of the sources that should be looked at in live detectors. Is these collapses is not the most unfortunately, is not the one that has more probability of happening. I think this one event every 50 years or something like that. So we should be lucky enough to see that. But the thing is that this is proposing that you will have a modification to the gravitational signal, because instead of having the ring down phase, then it will start to get some of the radiation that was in the standard picture. It's coming into the black hole. It doesn't come out. Here it would come out. In fact, people is also looking for echoes. Now this is a hot topic now in general relativity, and it's that some people, some astrophysicists, is trying to adjust templates with echoes, even in the cases of binaries. You have two binaries, and you assume that instead of being from the first two black holes, these are two ultra-compact stars. Then they collide, and then they said, well, maybe because there are not real black holes, again, there is some signaling which is in the form of echoes. So there has been a very interesting paper in which they see that the first detections of black hole colliding is better adjusted by these echoes templates. But the thing is that the LIGO people replied, and it's a matter that right now this detection is just in the less than 2 sigma, meaning that the people of LIGO say, well, there's no significance at all. So, but the other people is, well, if we accumulate more observations, maybe we realize that this is the case. And just to finish, the thing is that once I give you this example of electromagnetism, then the idea is to see whether we are able to do the same thing for gravity of all the stages. But what we have done is that instead of starting from the start, for example, saying that let's try to make instead of a peak condensation, let's do a decondensation, so that the initial definition of the vacuum state already has enough degrees of freedom to cover up a metric instead of we cover up just an electromagnetic field. Instead of doing all these things, what we are doing is to see which are the main differences between electromagnetism and gravity, and see which are the problems that we will find in all this way, and to try to solve some of those problems. Even without, as I say, without prescribing all the microscopics of. And then there is this nice paper of Carlip, in which he was kind of reviewing problems that emergent gravity theory could have to deal with, and I have put most of these challenges plus some of the challenges that I think myself that there are there, and in these challenges, I have just put a sentence saying that right now I am working with several of these problems, trying to see whether there is specific solutions to that, and of course these are not all of them. These are challenges, but right now I would not say that there is a no-go thing that. For example, this one of the things that everyone, this Weinberg-Witten theory. There is always, when you go to a conference, there is someone that tells you you can't do that, because there is the Weinberg-Witten theorem that telling that it is not possible to build up gravitons from whatever thing that you start from. But then, if you go to this theorem and you see, so by rephrasing it to myself, we see that the very essence of Weinberg-Witten theorem is that there is something which is there even at the linear level of gravitons, and is that you cannot build a stress energy tensor for gravitons which is not gauge invariant. The thing is that you have first Pauli theory, you have gravitons in a Minkowski space, and it has this gauge symmetry there, and then you try to build up a stress energy tensor for this theory. This stress energy tensor is very different from the Maxwellian theory, meaning that the stress energy tensor itself is not gauge invariant. So it's like, immediately, it's like, well, I cannot associate easily energies to the different configurations in the system. So it's kind of, wow, what's happening here? But, for example, by embedding, this is one of the things that we're doing, by embedding the phase probability theory in a much bigger theory, in the same style as electromagnetism, in which you have terms that are breaking gauge invariance. What you get is that you have an entire theory which is not, that doesn't have the gauge invariance, then you analyze the distortionality tensor, and then now everything is perfectly well behaved. Different, so again, it has some symmetries, but these are not gauge symmetries. And then you see that the distortionality tensor distinguish between all of those, and you are happy because you don't have any, because you don't have gauge symmetries. You're happy with what you have. But then again, there are specific solutions in the space of the solutions of the entire theory. There are specific solutions because it happened the same. There are several fields that behave like free fields. These free fields, if you impose that there are zero, then what happened is that now, again, the symmetries that were not real symmetries now behave as real gauge symmetries. But the difference with the electromagnetism is that now the stress energy tensor maintain the idea of distinguishing something of before. Instead, in the Maxwellian case, the stress energy tensor already decide to not distinguish between them. And that's funny because when you have that, it's like, okay, it's like in this case, the only difference is that the stress energy tensor is really kind of realizing where it's coming from, and that the former theory was not gauge invariant. But then the thing is that once from that you construct the entire nonlinear theory, you end up with something that make consistent make consistent that you don't have operational meaning to these stress energy tensors. When you make when you start to couple gravity with itself, at the end of the day, what happens is that you don't have any operational meaning to associate any physical thing to the very stress energy momentum tensor with which we started with. So at the end, it's like, okay, who cares? So it's just to give you a flavor of the kind of, and then, so there are many things that we have to solve because one thing is the linear problem, then the nonlinear problem is much more complicated. So you have to find an important thing that has appeared several times here, but maybe rephrased in a different way, is that why there is just one single metric in your system. You can have systems that are more complicated in which there are more metrics. Or why your metric is really this strong equivalent principle that you were mentioning. In a sense here, it can be rephrased by saying that you have some sort of universal coupling to gravity. There is just only one thing that is acting as a metric, and everything else is coupled to this thing in the same way. So there are already hints that this is kind of the only way to do things. By, for example, there is this theorem by Weimer also, this soft Graviton theorem that is telling you that once you have a graviton and you have something else, the only consistent way to couple all these things is that all the rest of the fields are coupled in the same way to the gravitons. So at the end of the day, all of these ideas are kind of a decoupling issue. Is that you have some theory that has much more degrees of freedom, or it has some physics, but at the end of the day, is that in some low energy corner, many of these degrees of freedom, you are not able to touch them, or you are not able to grasp them. And probably I will finish with this. There is this question, for example, there is something that, for example, people do not like of these approaches, and people say, well, this means that we have to assume, for example, this Newtonian world. So in a sense, it's going backwards. It's like, well, we have this nice relativistic picture of reality, and now you are telling me that you are using fiduciary structures that are similar to the Newtonian worlds. And also, if that these structures is like, why you don't touch them? Why they, in a sense, are acting in something, but then you do not back react on them. So, first of all, I have to say that I'm not defending a Newtonian world with this analysis. As I said, it's just a test. It's a very simple scenario in which you can work out things. But what I am defending is that maybe there are different layers in physics, so that first of all, there is something that is pre-geometric, in terms of space at least, time for me is even a more complicated issue. But imagine that time is there, one time, not the one that we measure. That is time that serves to change. Then there is something that builds up the space, three-dimensional something. And then imagine that this is just a rigid structure from the lower energy degrees of freedom point of view. It's something that is kind of an S3. Imagine that you have something that topologically is an S3. It's something that is made of these atoms or something. And then imagine that you just make a sort of Einstein universe, but in a Newtonian way. That you have this sphere plus time. And then in this thing, there is these atoms already. And then you can work out all of what I have been saying. And then gravity will be only, and all of the particle physics, all of what we are used to, will be just the low energy corner of the vibrations, the description of the vibrations of this network, which is made of different things. So this is more or less, it will be a possible scenario to work out. We're just starting to work out many specific details on the process. So again, to final words is that there are still many issues to fully understand. But as I said, my experience right now is that every time that I found something that is, this is a no-go way, when you analyze it carefully, it's not a no-go. Instead, it has a lot of physics into it. But there are ways at least to continue seeing whether these obstacles are final or not. And in any case, I think that I see this way of proceeding not as the way that not as something that is the only way. I think it's a complement to, for example, principal theories. I think that principal theories have been fantastic in physics many times in history. So I don't say that this shouldn't be applied. I think that these ideas that sometimes I compare this as Lorentz versus Einstein. It's like these Lorentzian things, at least in my studies, it was always been like this card that you're like, this guy start to deal with microscopy and then everything it wouldn't go anywhere. But I think that at some point, these two, there are other examples in history in which precisely because they work like this, they were able to do something important. So what I am advocating is that we have to be more into trying to maintain an equilibrium between approaches which are more principle-based and approaches in which are more kind of constructive. So that's all. Thank you very much.
Okay, we have a few minutes for questions.
Sorry.
Yes, Patrick.
I'm quite interested in what you said about this phase where black holes morph into white holes. Can you elaborate a bit, please, on the consequences for gravitational wave phenomena? So something that really comes to my mind is, I guess I'm primordial black hole. I'm going to go with something similar, and I would expect if they also suddenly turn into white holes, this would somehow manifest itself in the stochastic backgrounds.
Well, these are two different issues, because some people think that in the moment in which you prescribe that some black hole becomes a white hole, it means that you are kind of seeing in the sky a signal or something that you can look at, which is a possibility. But in these cases, the most simple situation is not that, because when you have a neutron star, for example, the more idealistic situation is that the neutron star collapses and goes back to the same position. If you don't add dissipation, you just go back to the same. So from far apart, you will not see anything. It's only the dissipation that it will throw some. Is that some things would continue in a collapse and expand, and some other. Similar to a supernova, a normal supernova that is forming a neutron star. In a supernova, what happens is that you have the matter collapses and then some shells are thrown away, and then these are the things that you see. But there are a core that stays there. So here is kind of the same. Is that what you see is that the process itself of forming one of these objects has a very short transient, very short in terms terms of astrophysical terms. And then, so these white hole black holes, you don't see them in terms of a proper phenomenon. The explosion is the process itself. It's the collapse itself of the structure. You have a star, it collapses, and then this leads to a lot of physics. And what we are analyzing here is that within all this physics, there is specific physics related to the very core in which something has been built up. So whether it's a black hole, or in our case, we are defending that instead of being a black hole, it should be one of these.
So does it leave any traces in the gravitational wave stochastic backgrounds?
Well,
I mean, that would be
you mean in the stochastic background?
Yeah, that's what I had in mind.
Yeah, well, that's that you know that this is very complicated because for that you need that there is either up to now we don't have any trace of primordial black holes. So you will need that some stellar things, that some primordial black holes are already there for ages. This is more in the spirit. I don't know, but this is more in the spirit that the first stars were built up in a particular generation, and then black holes is something that has been built up recently as a further process of collapse of different structures. This is more around this line.
Barcelo.
Yeah, thank you for the talk. Maybe just on this also, your motivation is mainly from the kind of condensed matter way of thinking you were mentioning at the beginning of the talk, right? The motivation for these bouncing scenarios.
Yeah, the original way in which I believed to this scenario was based on this.
So it's interesting because it seems to be a different motivation from the ones of other people, like as we talk like Rovelli and these other people are coming to the same kind of conclusion. They have other motivations and they can,
well,
after you.
No. In fact, they reach this thing, but they are coming from the idea of in the case of Rovelli groups is that they are coming more into because the bouncing scenarios in cosmology. When you analyze how something collapses, the simplest scenarios of collapse is that the internal part, the one that is described like matter, is very similar to a cosmology. And then because you have quantization loop quantum cosmology, quantizations of cosmological models in which you have bounds, they say, well, maybe in a black hole you have the same thing. But the thing is that in a black hole you have a different peculiarity because you have the cosmological region, but you have also the external region that you have to paste. And then the problem is that when the things are collapsing, the light comes, you are tilting them. And then when these things start to try to bounce, it has to fight in a cosmological scenario, there is no outside, so it has not to fight to anything. So then it leads directly to a time symmetric bounce. Instead, in the black hole case, the thing is that there is kind of what happened? This tends to bounce back, but then there are these light cones that you left behind that do not allow you to connect causally with outside. And then in this tension, what Rovelli has done is kind of relaxing this tension a bit, just a bit, saying that how he was thinking how to make these two things consistent. And he said maybe what happens is that the observers that are sitting in the object itself, they will see everything in a very quick time, and they will see this as a cosmological way. But the observers that are outside, they will see this as something that happened there, but they don't see this for ages as a black hole. And it is consistent with the black hole idea. This is the take of, and this is the big difference between the Rovelli approach and us. Because our approach is that no, this thing is seen by the observer outside. The difference is that our time scale is so short that if it is there, it will be seen. It's not something that is, again, this is formed part of my way of researching, because it's like in black hole physics there are many things that you can propose, but there is no way to sorry.
Can I ask you a question about that? I'm not entirely sure I understand your answer. Maybe I should try to. So, if I remember correctly, is the conformal diagram that they usually draw is, isn't it something like this? So here's the collapsing matter, and then you have the quantum gravity region, or something, whatever it is, and it
Yeah.
somehow tunnels through, and then here's the white hole
Yeah.
up here. Couldn't you have observers that somehow, go around and they would see, so that in the sense that this would be in their causal past at some point, at least part of that event, so that they could see some signature of that in the Rovelli picture as well?
Yeah,
Or-
I mean,
Maybe that's, I misremember, but I think it's
no.
something like that.
Rovelli has two different models, but
Okay.
in the model that is more similar to us, this region, if you eliminate this idea that maybe even it is not possible to describe this as a geometry, but maybe imagine that there is a semi-classical description of that.
Okay.
Then there are two regions of closed-loop time-like curves, one here and one other here. No? One which are kind of black hole-likes, and another region which is white hole-like.
Okay.
And this doesn't matter, but the thing is that you are right that observers could see these things. But the difference between Rovelli and us is that this thing is such that it lasts, in temporal terms, this region is lasting so much from the external point of view of someone that is sitting here,
Oh, right, okay. And
that
yours-
the only ones that are able to see a ray that is coming from here, from the white hole, there are observers that are living in ages and ages, the age of the universe. Instead, our proposal is precisely the one that you said, is that this happening in times that an observer, a real astrophysical observer, would see. So, in a sense, I'm defending this model in the sense that at least it tells you something that someone, at some point, not tomorrow, but in 100 years' time, someone will say, you are wrong, or not.
Whereas
But
Rovelli-
as the Rovelli model, nobody could say that is wrong.
Yeah. Because he
All
takes
the entire-
this as a good feature because he then says that's the reason why we don't see this, because it's too long.
No. In this case, because it's too long, it meaning that for an astrophysical, for someone that is working in astrophysics, the model of Rovelli is they don't care. It's like, for me, this is a black hole, and I don't mind whether this is your model or whether this is an evaporation more on the initial style of Hawking or whatever.
But from what I understand is they've tried to come up with some sort of phenomenology where they say that there should be traces,
Exactly.
in principle at least observable in radio astronomy.
The thing is that the original Hawking evaporation, it goes with a time scale which is m to the cube. Instead, this evaporation, the one proposed by Rovelli with other arguments, it goes with m to the square, meaning that you are taking a lot of orders of magnitude with respect to the Hawking one. And then this acts strongly on primordial black holes, meaning that you don't have the constraints to primordialities are much less restringent because it takes less time for this to happen. And then there are objects which can be larger. You have more range of masses of primordial things that could lead now to some signals. And that's why they work out some phenomenology. But the phenomenology of Rovelli is based on primordial things. Is that it has to be something that happened there, and that now we are lucky enough that they are now happening in the last stages of evaporation. Or decay. So this is and that's why they have, with respect to Hawking is, this is impossible to see anything.
Yeah.
It's almost discarded that to see, maybe it's right, but we will not see it.
Yeah, against the
In this
cosmic
case,
background.
maybe it's closer. But the difference in our case is that our time scale is going, we say that there is a fast channel which goes with M, steep line, and then there is Rovelli. And then it's Hawking, which again is the same thing. Which is it's nice to see that there is just the difference in these coefficients. But this, because the huge difference between a astrophysical black hole and a mass Planck, it makes that this goes with 10 to the 70 years of the universe, this goes with 10 to the 30 years of the universe, and this one goes 10 to the minus 6 seconds.
Okay. Good. I think we've exhausted the time. Thank you very much.